Welcome back. In this video, we're going to talk about biasing. And biasing is simply setting the transistor at a particular operating point. So the concept of biasing simply means setting the operating point, also known as the quiescent point, or simply the Q point for the transistor. The way we bias the transistor is by connecting external components and sources. And so a typical biasing configuration might look something like this. I have a BJT transistor, in this case an NPN, with my collector, base, and emitter. And I'm going to connect my collector terminal to a VCC supply via resistor RC. And then I'll also connect that to my base terminal through a resistor RB. And I'll connect my emitter terminal to ground. We already saw from the IV characteristic that there are different regions of operation for the transistor, and depending on our application, we are going to want to place a transistor in one or a different region of operation. For example, for switching or digital applications, we are going to want to switch the transistor between cutoff and saturation. For linear amplification, we are going to want to place the transistor in the linear active region. Within the linear active region, if you remember, there's a family of curves, and so there are multiple points within those curves that will fall within the linear active region. However, there's going to be some undesirable consequences if we place those points very close to a different region, for example, like saturation. Let's take a look at the IC curve, the IV curve, so that we remember that. And so we have our curve of the collector current versus the VCE voltage. And if you recall, this was a family of curves. There is the cutoff line, and then as we increase IB, we get different lines for IC. So this will be the direction of increasing IB. And for each one of those lines, we have that if our VCE voltage is less than the VCE saturation, which is around 0.3 volts, then we're in the saturation region. If it's greater than that, we're in the linear or active region. And otherwise, we can be in the cutoff region, where IC is equal to 0. Now, like I said, within these lines, there are multiple possibilities for an operating point within the linear active region. We can be, for example, in this point right here, or we could be in that point up here. They're both in the linear active region. However, when I'm doing amplification applications, what I'm doing is I am applying an AC signal on top of my DC bias point, and so I'm basically moving my signal around that Q point, around that quiescent point. And what that translates into is, in the case of this point here in the middle, I will be, switching the levels of my signal around that Q point. And the same thing will happen with the one up here. Now notice that up here, if I switch the signal or if I move the signal too much around that Q point, I will be going in and out of saturation. So we wouldn't consider that a very robust quiescent point if we need to vary our signal widely. Whereas this one is a much more robust quiescent point. And normally we're going to try to do that. We're going to try to center our quiescent point within the linear region so that we have maximum outputs or signal swing. Now, the set of different available operating points is given by what's known as the load line. The load line is just a graphical representation of all the possible Q points. The way the load line is calculated is by applying KVL around the collector emitter path. KVL being Kirchhoff's voltage law around collector to emitter path. And so for this simple case that I've represented here, our KVL equation will look as follows. If I apply through the collector emitter path, I start up here and I have VCC minus the voltage drop across the RC resistor, which is ICRC, minus the voltage drop across the transistor, which is VCE. That's equal to 0, and I can solve that for IC. I have IC is equal to VCC minus VCE divided by RC. Now, to calculate the load line, we are going to do that using the 2 points. Remember, 2 points define a line. The 2 points that lie on the intersection of the axis, the x-axis, VCE, and the IC or y-axis. And so this point corresponds to the condition of IC being equal to 0, and this point up here corresponds to the condition of VCE being equal to 0. Once I calculate those 2 points, I can join them, and that will give me my load line. Let's go ahead and calculate them just for here. If I wanted to calculate the point down here, crossing the VCE axis, I will need to set the condition that IC is equal to 0. So first I'm going to set IC equals to 0 and solve in that equation. IC equals to 0 implies VCC minus VCE over RC is equal to 0, which implies VCE minus VCC is equal to 0, and therefore VCE is equal to VCC. And second, I'm going to set VCE equal to 0. And so I'll have that IC in that case is equal to VCC minus 0 divided by RC, or equal to VCC over RC, which I have that point over here being VCC over RC. Let's put some numbers just to give ourselves a sense of example here. Let's imagine my VCC is equal to 10 volts. And my RC is equal to 5 kilo ohms or 10 kilo ohms, just to make the math easy. Okay. In that case, for our example, we will have that in condition 1, IC is equal to 0, implies VCE being equal to VCC, which is 10 volts. And in the second one, we have VCE is equal to 0, implying IC is equal to VCC, which is 10 divided by 10K, or is equal to 1 milliamp. Okay, so this point here will be 10 volts in our example. Trying to find a color that hasn't been used, but I guess I can't. So this will be 10 volts here, and this will be 1 milliamp. Okay, and when we're looking for our Q point, again, we're going to want to have it centered, and so if we think about that, this might be somewhere at half a milliamp and 5 volts, for example. And that will be our quiescent point. We're going to be talking about different possible biasing configurations, and there are going to be some that are better than others. We're going to learn how to evaluate them, but also we are going to sometimes see biasing configurations that are better for particular applications or for particular conditions. One of the things that we're going to focus when we design a biasing configuration, a biasing network, is stability of the biasing point. We don't want the quiescent point that we set, the nominal Q point, to vary depending on external circumstances. One of the key parameters that we're going to consider variations about is the beta of the transistor. We studied the beta as the forward current gain, or the ratio of IC to IB. And so we have beta, and we said this was the forward current gain of the transistor. Now, beta is a parameter that depends on process parameters, and so it can vary widely for a given transistor. So if you pick two transistors from the same batch, you will find two different values of beta. When you look at the datasheet, the range is pretty wide. For a 2N3904, that is the datasheet that's provided on your course website, you can see that beta varies somewhere between 50 to 300. Again, that's a pretty large range, and so you don't want to find out that you designed your biasing network to have an operating point at a certain place, and that simply because you picked, one transistor that didn't have a nominal beta of 100, but it was more close to 200, now your Q point all of a sudden is in the saturation region. So you want to design a biasing network that's going to make your Q point robust to beta variations. And we're going to see different configurations, as I mentioned, and we're going to see how different configurations are more or less robust to these variations. Thank you.